We live in a universe teeming with light and wonder, a cosmos of glittering stars, swirling galaxies, and vibrant nebulas. From the dust motes dancing in sunbeams to the grand superclusters spanning billions of light years, our senses are constantly awash with the incredible tapestry woven by visible matter. Yet this entire breathtaking spectacle, all that we can see, measure, and interact with, constitutes a mere fraction of existence. Imagine looking out at the universe, perceiving only the faint glow of a faraway lighthouse, while an entire ocean of unseen forces and substances surrounds it. This isn't just a metaphor. It's the profound reality of modern cosmology. Our most precise measurements tell us that everything we comprehend, all the atoms that form planets, stars, and even ourselves, accounts for an astonishingly small portion of the universe's total contents. For centuries, humanity has observed the cosmos with growing sophistication, from naked-eye observations to powerful telescopes pushing the boundaries of what's observable. We've charted celestial bodies, understood stellar evolution, and mapped the distribution of galaxies across vast distances. Each discovery deepened our understanding, yet simultaneously, it unveiled a more profound mystery lurking beneath the surface of what seemed to be a complete picture. The universe we inhabit is not primarily composed of the familiar elements detailed on the periodic table. Instead, an overwhelming 95% of its mass and energy exists in forms that remain utterly mysterious to us, entities we cannot directly detect, touch, or even fully comprehend. They interact with our observable universe only through the subtle pull of gravity, leaving their indelible mark on the cosmic evolution. This profound cosmic imbalance is not a speculative theory, but a conclusion drawn from decades of rigorous scientific observation and intricate mathematical models. It's built upon evidence gathered from the most distant corners of space and time, from the earliest moments of the Big Bang to the present-day expansion of our own galactic neighborhood. Our journey into the invisible universe begins with the familiar, the mere 5%. This sliver includes every atom that makes up you, me, the air we breathe, the solid ground beneath our feet, and every star, planet, and galaxy that we can detect across the observable cosmos. It is the realm of ordinary or baryonic matter. Baryonic matter consists of protons, neutrons, and electrons, the fundamental building blocks of atoms. These particles, bound together by the strong and electromagnetic forces, form the intricate structures we observe. This includes the hydrogen and helium forged in the early universe, and all the heavier elements cooked inside the hearts of stars. We see this baryonic matter because it interacts with electromagnetic radiation, light. Stars blaze with fusion, emitting a spectrum of light we can capture with telescopes. Galaxies glow with the cumulative light of billions of stars, revealing their majestic spiral arms and elliptical forms. Even the tenuous gas between stars can be observed as it absorbs or emits specific wavelengths of light. From radio waves charting the distribution of cold gas to X-rays revealing superheated plasma in galaxy clusters, our instruments allow us to paint a detailed picture of the visible universe. This observable 5% is a vibrant, dynamic arena of cosmic evolution, where galaxies collide, stars are born and die, and planets potentially harbor life. Consider the familiar structures, like our own Milky Way galaxy. It's a vast cosmic island of hundreds of billions of stars, gas, and dust. We can map its arms, identify its black hole center, and even track the motions of individual stars within it. All of this forms part of the visible 5%. Yet, despite its immense scale and complexity, the visible universe presents a grand paradox. For decades, astronomers observed phenomena that simply couldn't be explained by the amount of ordinary matter they could see. It was like watching a weightlifting competition where the lifter moved impossible weights with ease. suggesting an invisible force was aiding them. The first whispers of this cosmic enigma emerged in the 1930s from the sharp observations of Swiss astronomer Fritz Zwicky. He was studying the velocity of galaxies within the Coma Cluster, a massive collection of thousands of galaxies bound by gravity. His findings were truly astonishing and baffling, revealing an unexpected discrepancy. Zwicky measured the dispersion of velocities of galaxies within the Coma Cluster. He assumed that these galaxies were gravitationally bound, meaning their collective motion balanced the cluster's self-gravity. Using the virial theorem, he could estimate the total mass required to hold the cluster together based on how fast its galaxies were moving. His calculations showed that the cluster needed to contain far more mass than could be accounted for by the visible light from its galaxies. In fact, he estimated a deficit of nearly 400 times the visible mass. He provocatively termed this missing substance Dunkel Materie, or dark matter, suggesting a dominant, unseen component. Zwicky's audacious claim was revolutionary, but it was largely ignored by the astronomical community for decades. The instruments of the time were limited, and the concept of such vast amounts of invisible matter seemed too speculative. Astronomers focused on what they could see and measure, rather than on abstract, unobservable components. The puzzle resurfaced with renewed vigor in the 1970s, thanks to the pioneering work of American astronomer Vera Rubin and her colleague Kent Ford. Her focus shifted from galaxy clusters to individual spiral galaxies, observing their rotation curves with unprecedented precision. These observations would provide the most compelling initial evidence for dark matter. Rubin and Ford used spectrographs to measure the velocity of stars and gas at varying distances from the centers of spiral galaxies. Based on Newtonian physics, one would expect stars further out from the galactic center, where most of the visible mass is concentrated, to orbit more slowly, much like planets further from the Sun. But what Rubin and Ford found was profoundly different. They consistently observed that stars and gas on the outer edges of galaxies were orbiting just as fast, or even faster, than those closer to the center. This defied all expectations based on the visible matter alone, creating a profound theoretical conundrum. This flat rotation curve implied that there had to be a significant amount of unseen mass, extending far beyond the visible boundaries of the galaxy, creating an additional gravitational pull. This invisible halo of matter was needed to explain the sustained high orbital speeds of distant stars. Rubin's meticulous observations were performed on numerous galaxies, repeatedly yielding the same inexplicable result. This wasn't an anomaly in one measurement. It was a universal pattern, firmly establishing the rotational curve anomaly as a fundamental property of spiral galaxies. The concept of dark matter was no longer a fringe idea. The evidence for dark matter didn't stop with galactic rotation curves. One of the most visually stunning pieces of evidence comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Massive objects, whether seen or unseen, warp the fabric of spacetime around them. This warping effect acts like a cosmic magnifying glass, bending the light from distant background galaxies as it passes through the strong gravitational field of foreground galaxy clusters. We observe these background galaxies as stretched, magnified, or even multiple, by analyzing the degree of distortion in these lensed. This discrepancy between visible light and gravitational mass is glaring. The lensing mass needed to produce the observed distortions is several times greater than the luminous mass, providing independent and powerful confirmation of vast amounts of unseen matter pervading these cosmic colossal structures. Perhaps the most iconic piece of gravitational lensing evidence comes from the Bullet Cluster, a monumental cosmic collision between two galaxy clusters over 150 million light-years away. This event provided a critical test for the dark matter hypothesis. When these two clusters collided, their ordinary matter, primarily hot gas, which makes up most of the visible mass of a cluster, interacted with each other, slowing down and leaving a distinct wake. This hot gas, visible in X-rays, constitutes the bulk of the baryonic matter in these clusters. However, the dark matter, which doesn't interact electromagnetically, would simply pass through itself without slowing down. It would act like ghosts, slipping past each other while the ordinary matter collided and lagged behind. This distinct behavior would offer a direct observational signature. And indeed, observations of the Bullet cluster revealed precisely this. The map of gravitational mass, derived from gravitational lensing, showed it was located separately from the peak of the X-ray emitting gases. The dark matter had passed through while the gas had been slowed. This spatial separation of gravitational mass from observable baryonic mass is considered by many cosmologists to be the most direct observational proof for the existence of dark matter. It severely constrains alternative theories that try to explain gravitational anomalies by modifying gravity instead of adding new matter. Another cornerstone of evidence for dark matter comes from the cosmic microwave background, or CMB. This ancient light, a faint echo of the Big Bang, provides a snapshot of the universe when it was only 380,000 years old, an infant universe only just cool enough for atoms to form. The CMB is not perfectly uniform. It contains tiny temperature fluctuations, or anisotropies, which represent the initial density variations that eventually grew into all the stars and galaxies we see today. These ripples are crucial clues to the universe's early composition. Detailed analysis of the angular size and amplitude of these fluctuations, captured by missions like WMAP and Planck, provides incredibly precise information about the universe's fundamental parameters, including its geometry, age, and most importantly, the relative proportions of ordinary matter, dark matter, and dark energy. The peaks and troughs in the CMB power spectrum, a mathematical representation of these fluctuations, are directly sensitive to the sound waves that propagated through the primordial plasma. The shape of these peaks tells us precisely how much baryonic matter versus dark matter was present. If there were only baryonic matter, the patterns in the CMB would be significantly different. The observed pattern of peaks confirms that dark matter was absolutely essential in seeding the structures we see. It provided the gravitational scaffolding without interacting with the radiation or gas. Without dark matter, the gravitational wells necessary to pull together early matter would have been smoothed out by the pressure of radiation. But dark matter, being impervious to radiation pressure, could form denser clumps, acting as gravitational anchors for ordinary matter to fall into. This crucial role of dark matter in early structure formation extends to the larger-scale distribution of galaxies in the contemporary universe. Computer simulations of cosmic evolution demonstrate that without dark matter, the universe would look very different. Observations show that galaxies and galaxy clusters are not randomly scattered. Instead, they form a vast, intricate cosmic web of filaments, sheets, and voids. This network is a direct consequence of the gravitational collapse of primordial density fluctuations, predominantly driven by dark matter. Baryonic matter would have been too bouncy to form such massive structures in the time available since the Big Bang. Its interactions with light would have prevented it from clumping sufficiently fast. Dark matter, on the other hand, could have started clumping much earlier. Simulations that include the measured amount of dark matter accurately reproduce the observed cosmic web, galaxy cluster abundance, and their distribution. Without dark matter, the simulated universe would be far too uniform, lacking the clumpiness we observe. So we have compelling evidence from galactic rotation, gravitational lensing, the cosmic microwave background, and larger-scale structure. All point to the existence of a substantial amount of unseen matter. But what is it? What are its properties? We know what dark matter is not. It's not ordinary baryonic matter. It doesn't emit or absorb light, otherwise we would see it. It also doesn't interact strongly with light or other baryonic particles, which is why it passed through itself in the bullet cluster. It's not cold gas clouds, which would glow in specific wavelengths or absorb background light. It's not dust, which would dim the light from distant objects. It's certainly not normal stars or black holes, as we could detect their luminous output or gravitational influence in a way that doesn't match the observed distribution of dark matter. Could it be very faint, unseen objects like rogue planets or failed stars, brown dwarfs, or even primordial black holes? These are collectively known as MACHOs, or massive astrophysical compact halo objects. Early searchers looked for these. MACHOs can be detected through microlensing, where their gravity momentarily magnifies a background star as they pass in front of it. While some microlensing events have been observed, they account for only a tiny fraction of the expected dark matter mass, largely ruling out MACHOs as the primary component. The current leading hypothesis is that dark matter consists of new, exotic particles not found in the standard model of particle physics. These particles are thought to interact only very weakly with ordinary matter, primarily through gravity and possibly the weak nuclear force. The most popular candidate for dark matter particles are WIMPs, or weakly interacting massive particles. These theoretical particles are generally thought to be many times more massive than a proton, but interact so rarely that they pass straight through ordinary matter without leaving a trace. If WIMPs exist, they would be constantly streaming through us, through the Earth, and through every object in the universe, almost entirely unnoticed. Their weak interaction is what makes them dark and so difficult to detect. Scientists are actively engaged in various experiments to directly detect WIMPs in Earth-based laboratories. These detectors are built deep underground, shielded from cosmic rays, to maximize the chances of sensing the incredibly rare interaction of a WIMP with an atomic nucleus. When a WIMP potentially strikes an atomic nucleus in the detector, it would cause a tiny recoil, like a billiard ball hitting another. This minuscule energy transfer is what these highly sensitive experiments are designed to observe, looking for the faintest flickers of light or charge. Another class of dark matter candidates are axions. These are much lighter than WIMPs and were originally theorized to solve a different problem in particle physics related to the strong nuclear force. If they exist, they would also interact very weakly with ordinary matter. Axion dark matter could potentially be detected by converting them into photons in strong magnetic fields. Experiments are actively searching for this conversion, hoping to pick up on these elusive particles, which could explain the cosmic missing mass. Other candidates include sterile neutrinos, which would be non-interacting versions of the familiar neutrinos, and even primordial black holes formed in the very early universe, though current evidence limits their contribution compared to WIMPs or axions. Beyond direct detection, scientists are also pursuing indirect detection, looking for the annihilation or decay products of dark matter particles in space. If dark matter particles collide or decay, they could produce gamma rays, neutrinos, or cosmic rays that we could detect. Telescopes like the Fermi Gamma Ray Space Telescope are meticulously scanning the sky for such signals, particularly from regions rich in dark matter, such as the galactic center or dwarf galaxies, where dark matter density is expected to be high. Finally, particle colliders like the Large Hadron Collider could potentially create dark matter particles in high-energy collisions. If produced, they would carry away energy and momentum, leaving a distinct missing energy signature in the detectors. Despite decades of searching, dark matter particles remain elusive. No definitive detection has been made, adding to the cosmic mystery and fueling intense scientific debate and further experimental ingenuity. The journey to unveil this unseen universe continues. Now, having explored the gravitational phantom known as dark matter, we turn to an even more enigmatic component of our universe: dark energy. While dark matter pulls things together, dark energy, remarkably, seems to be pushing the universe apart. Just as the missing mass problem pointed to dark matter, a new cosmic crisis emerged in the late 1990s from observations of distant supernovae. These celestial explosions, specifically Type Ia supernovae, serve as invaluable standard candles for measuring cosmic distances. Because Type Ia supernovae are thought to explode with a consistent peak luminosity, their apparent brightness can tell us how far away they are. Fainter supernovae are further away, and brighter ones are closer. This allows astronomers to map the expansion history of the universe. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, observed distant Type Ia supernovae and made a truly shocking discovery. The supernovae were fainter than expected for their measured distances. This meant the galaxies hosting these supernovae were actually further away than they should have been, given the standard models of cosmic expansion. The most astounding conclusion was that the universe's expansion was not slowing down due to gravity, as expected, but was, in fact, accelerating. This discovery was so profound and unexpected that it earned the lead researchers the Nobel Prize in Physics in 2011. It introduced the concept of dark energy, a mysterious force or property of space itself, responsible for this cosmic acceleration. This groundbreaking finding completely redefined our understanding of the universe's destiny. Before, cosmologists debated whether the universe would eventually collapse in a big crunch or expand forever at a slowing rate. Now, the accelerating expansion suggests a different, more isolated future. The existence of dark energy gained further compelling support from complementary observations of the cosmic microwave background. Just as with dark matter, the precise patterns in the CMB's temperature fluctuations offered insights into the universe's energy content. The specific peak heights and spacing in the CMB power spectrum are highly sensitive to the total energy density of the universe. The measured properties of the CMB independently confirmed the need for a dominant component that acts as a repulsive force. Another key piece of evidence comes from baryon acoustic oscillations, or BAO. These are fossilized sound waves from the early universe, imprinted on the larger-scale distribution of galaxies today, acting as yet another standard ruler. During the early universe, before recombination, pressure waves propagated through the photon baryon plasma, creating regions of slightly higher density. When the universe cooled and atoms formed, these sound waves stopped, leaving a characteristic statistical preferred separation between galaxies. By measuring this preferred separation between galaxies at different cosmic epochs, astronomers can map the expansion rate of the universe over time. The BAO measurements consistently confirm the accelerating expansion seen with supernovae. So multiple independent lines of evidence, Type Ia supernovae, the cosmic microwave background, and baryon acoustic oscillations all converge on the same astonishing conclusion. The universe's expansion is accelerating, driven by dark energy. But what is dark energy? Unlike dark matter, which is thought to be particles, dark energy is widely believed to be a property of space itself. It's often equated with Einstein's cosmological constant, a concept he famously introduced and then abandoned, only for it to be resurrected spectacularly. Einstein initially introduced the cosmological constant to make his general relativity equations admit a static universe, as was believed at the time. When Edwin Hubble discovered the expansion of the universe, Einstein supposedly called it his biggest blunder. How can empty space have energy? Quantum mechanics suggests that even a vacuum is not truly empty. It's filled with virtual particles constantly popping in and out of existence, creating a vacuum energy. This intrinsic energy would exert a repulsive force. If this vacuum energy is indeed dark energy, it represents a colossal mismatch between theoretical prediction and observation. Theoretical calculations predict a vacuum energy density vastly larger than what is observed, differing by an astounding 120 orders of magnitude. This is known as the cosmological constant problem. This enormous discrepancy has led scientists to explore alternative explanations for dark energy. One idea is quintessence, a dynamic, evolving energy field that fills space, similar to a scalar field, whose energy density could change over time. Another possibility is that dark energy is not a new form of energy at all, but a breakdown of general relativity on vast cosmic scales. Perhaps our understanding of gravity needs to be modified, leading to modified gravity theories. However, modified gravity theories face significant challenges in reproducing all the observed cosmic phenomena, including the successes of general relativity on smaller scales and the precise details of the CMB and the Bullet cluster. The exact nature of dark energy remains one of the greatest mysteries in modern physics. Its existence forces us to confront fundamental questions about the nature of space, time, gravity, and the ultimate fate of the universe. Let's recap our cosmic inventory. Ordinary visible matter, everything we can touch, see, or measure, from galaxies to dust, including us, accounts for a mere 5% of the universe's total mass and energy. Dark matter, the invisible gravitational glue that holds galaxies and clusters together and seeded larger-scale structures in the early universe, comprises roughly 27% of the total. It is the dominant form of matter in the cosmos, and the most pervasive, yet utterly mysterious, component is dark energy, the repulsive force driving the accelerating expansion of the universe, making up a staggering 68% of the total cosmic energy density. This is the modern cosmological consensus, the lambda-CDM model, named for the cosmological constant, lambda, representing dark energy, and cold dark matter, CDM. It's the standard model of cosmology, incredibly successful at explaining a vast array of astronomical observations. The lambda-CDM model successfully predicts the larger-scale structure of the universe, the peaks in the CMB, the abundances of light elements from the Big Bang, and the accelerating expansion. It's a testament to decades of scientific endeavor. However, the model relies on two components, dark matter and dark energy, for which we have no direct detection or definitive understanding of their fundamental nature. This makes the lambda-CDM model arguably an incomplete, albeit highly effective, description of reality. The quest to understand this invisible 95% is at the forefront of modern physics and cosmology. It's a grand scientific challenge that promises to revolutionize our understanding of the fundamental laws of nature and the very fabric of existence. One significant implication is that our standard model of particle physics, which describes all known fundamental particles and forces, is fundamentally incomplete. It accounts for the 5% of baryonic matter, but offers no explanation for dark matter or dark energy. This means there's new physics out there, beyond our current understanding, waiting to be discovered. Whether it's new particles, new forces, or a deeper theory of gravity, the existence of the dark universe points to an exciting frontier. Future experiments are being designed to push the boundaries of detection. Next-generation dark matter detectors, more sensitive and even more shielded, are being planned and built to increase the odds of a direct interaction. Telescopes like the Euclid mission from ESA and the Vera C. Rubin Observatory, formerly LSSD, will map the cosmic web and gravitational lensing with unprecedented precision, providing even tighter constraints on the distribution of dark matter and the properties of dark energy over cosmic time. The Square Kilometre Array (SCAR), a colossal radio telescope project, will probe the universe's larger-scale structure with unprecedented detail, potentially revealing more subtle clues about the distribution and influence of both dark matter and dark energy. Future particle colliders, even more powerful than the LHC, could someday achieve the energy necessary to produce dark matter particles in controlled laboratory settings, offering the first opportunity to study their properties directly. The hunt for dark energy continues on several fronts. New supernova surveys, precise galaxy clustering measurements, and advanced CMB experiments aim to refine our understanding of its behavior and density throughout cosmic history. The ultimate goal is a unified theory that can explain all aspects of our universe, integrating dark matter and dark energy seamlessly into a complete framework, potentially merging quantum mechanics with general relativity. The percentages, 5%, 27%, and 68%, are not static. The universe evolves. The relative densities of matter, both visible and dark energy, change as space expands. Early on, matter dominated. Today, dark energy is taking over. In the early universe, matter and radiation were far denser. As the universe expanded, matter's density diluted, radiation's density diluted even faster. Dark energy, if it's vacuum energy, remains constant in density even as space expands. This means that in the distant future, dark energy will completely dominate the universe. Galaxies that are not gravitationally bound to our local group will accelerate away from us so fast that their light will eventually stretch beyond our ability to detect it. Our cosmic horizon, the limit of what we can observe, will shrink, leaving only gravitationally bound clusters visible against an increasingly empty and cold void. This accelerating expansion paints a lonely, isolated destiny for our universe. The philosophical implications of discovering an invisible universe are profound. It humbles us, reminding us that our everyday reality, all that we can perceive, is but a tiny fraction of the grand cosmic truth. It signifies the vastness of the unknown, challenging our anthropocentric views and pushing us to expand our conceptual boundaries beyond the familiar. The universe is far stranger and more wondrous than we could have ever imagined. It also highlights the power of the scientific method. Despite the elusive nature of dark matter and dark energy, their existence was inferred and confirmed through meticulous observation, rigorous deduction, and the courage to challenge established paradigms. The realization that 95% of the universe is unknown motivates an entire generation of scientists to push the frontiers of human knowledge. It's a testament to our insatiable curiosity and our relentless pursuit of truth, wherever it may lead. The journey to unravel the invisible universe is far from over. It's a thrilling, ongoing saga of discovery filled with unexpected twists and turns. Every new observation, every refined theory brings us a step closer to a complete picture. Perhaps future discoveries will integrate dark matter and dark energy into a single, unified framework. Or perhaps they will reveal even more unexpected components, expanding the cosmic inventory beyond our current imagination. This mystery reinforces the idea that what we perceive with our senses is just a small window into a much larger, more complex reality. The cosmos is full of hidden depths, silent forces, and unseen substances that shape its destiny. The universe truly is a vast ocean of the unknown, and we are still navigating its shoals. The adventure of astronomy and cosmology lies in constantly challenging our assumptions and embracing the perplexing beauty of the unseen. So the next time you gaze up at the night sky, filled with countless stars, remember that this breathtaking spectacle, everything visible, is only 5% of the cosmic story. The true grandeur lies in the silent, invisible majority. This invisible universe of dark matter and dark energy is not just a scientific abstraction. It is the very framework upon which our visible reality hangs. It defines the past, dictates the present, and shapes the ultimate fate of all existence. The pursuit of these cosmic phantoms is a testament to the enduring human spirit of inquiry. We strive to understand, to uncover, and to bridge the gap between what we see and what truly is. It asks us to reevaluate our place in the cosmos, not as the center of visible creation, but as conscious observers within a much grander, largely unseen, and incredibly mysterious tapestry of being. The scientific journey is one of perpetual discovery, where every answer unveils new, deeper questions. The 5% we see is a remarkable gateway into the 95% we are only just beginning to grasp. This is the captivating narrative of our universe, a story far more intricate and surprising than any science fiction, continuously unfolding itself through the persistent dedication of countless minds. The cosmic microwave background, the faint echo of a universe only 380,000 years young, provided us the first precise measure of these components. It was our ancient baby picture, revealing the invisible hand. Our understanding shifts from a purely visible universe to one dominated by unseen forces, gravitational architecture, and a pervasive cosmic push. It's a profound paradigm shift in cosmology. The universe is not just what meets the eye. It's a complex interplay of the known and the unknown, inviting us on an eternal quest to comprehend its full, breathtaking reality. From the smallest atomic particle to the grandest galaxy cluster, the influence of the invisible is felt. It's a reminder that true understanding often lies beyond our immediate perception. The ongoing search for dark matter and dark energy embodies the core spirit of scientific exploration, venturing into uncharted territory, driven by anomaly and fueled by the promise of groundbreaking insight. What happens when we finally grasp the true nature of the invisible 95%? Our understanding of space, time, matter, and energy will be fundamentally transformed, ushering in a new era of physics. This documentary has embarked on a brief journey into the vast, unseen majority of our cosmos. It's an invitation for you to ponder the mysteries that lie beyond the stars, beyond perception. The universe is a cosmic enigma, a puzzle of astronomical proportions, and the pieces we've found so far tell us that the most significant parts are still waiting to be revealed. So breathe in the air, feel the ground beneath your feet, look up at the shining sun or the distant stars, and remember, you are part of the visible 5%, an island in an ocean of cosmic mystery. Thank you for joining us on this exploration of the invisible universe. May your curiosity continue to guide you through the wonders, both seen and unseen, that define our magnificent cosmos.